Okay, in this session, we're going to talk about the measuring architecture characteristics. Uh, of course, the software architecture is one of the important parts of software design and development, and we need to have a very good and comprehensive information about the software architecture and how to design it and how to manage it. In this session, we're going to specifically talk about the measuring the architecture characteristics. But before that, my name is Vahid Farahmandi. I'm born in Urmia, Iran, 1989. I have my BSc in Computer Software Engineering from Urmia University and in Medical Informatics MSc degree from Tariq Madaris University. I'm an international speaker and a book author. Currently, I'm working as the Chief Executive Officer at Previously, I have authored 3 books, Design Patterns in .NET, specifically on geof patterns. The other volume of my book is Design Patterns in .NET, which is focused on enterprise application architecture patterns. Both of these books were authored in Farsi or Persian language. And my third book is about .NET 7 Design Patterns and Depths, which is in English version. You can get access to it using the Amazon. It's published using the BPB publications. So let's start the session. We're going to measure the architecture characteristics. Before focusing on architecture characteristics, let's clarify some concepts. When we're talking about the software architecture, of course, we're talking about 4 different dimensions. First dimension is the use in our software. Today's are microservices or kernel-based architectural styles or the layer or tiered architectural styles. All these samples are architecture style. They are not our architecture. They're just our architecture style in our architecture. We have 3 other dimensions that we need to focus on them and clarify them in order to have good software, which is based on the business requirements and business needs. The second dimension in architecture is architecture characteristics, such as the performance, agility, testability, deployability, scalability, elasticity. All these characteristics needs to be analyzed in a software based on the requirements. We need to measure them. We need to find them and answer this question, why they are important and how they will affect our software. The third dimension is about the architectural decisions, which are our hard going to design the red lines in our architecture. And the fourth dimension is the design principles, which is the soft rules, where we can define the variants in our architectures. Okay, with these introductions, specifically, again, I said that in the session, I'm going to talk only about the architecture characteristics. And specifically, again, we're going to talk about measuring the architecture characteristics. So you can now find out that it's very little world of discussions that we're going to focus on it. So there are many more other concepts and discussions. You need to find them, you need to analyze them, you need to have good information about them. About measuring architecture characteristics, we have, of course, many problems while we are interacting with the architecture characteristics. One of the very important problems is the fact that these architecture characteristics are not physics. It means that we cannot touch them. When we cannot touch them, it means that we will not have very rigid information about the software characteristics. Of course, when we do not have any rigid information about it, or when we cannot touch something, there might be some ambiguity about that concept. For example, when we're talking about agility, it's very important to know that how does the architects going through architect design, architect the software for agility. We cannot touch the agility. We have no previous understanding about agility, so we need to describe it, we need to clarify it, and we need to resolve this ambiguity around this concept. The second problem around the definition of architecture characteristics is that there might be a varying of definitions around some concepts. For example, when we're talking about performance, the different roles in our teams might have their own definitions and their own understandings around performance. Software architectures might see performance as something which is totally different from what a software developer sees about performance. So we need to get into common definition. We need to put all our team members or all our stakeholders on the same page to have a common definitions around the concepts. And the third problem is that some characteristics might be too composite. The agility might be composed of different characteristics, such as modularity, deployability, testability, or other characteristics, which means that all these characteristics, when we put all these characteristics together, the agility comes into account and shapes its definition. So there might be some characteristics which are too composite. So we need to, again, clarify them. We need to decompose them and define each them, find a common definition for each of these characteristics. In order to solve these problems, we need to have objective definition. Objective definitions means that we need to find our ubiquitous language in our team. Ubiquitous language, in this case, means that we need to have transparency in software architecture characteristics definitions. We need to define the characteristics. We need to find a start point of them, the end point of them, how to measure them, how they affect our software. We all need to clarify this definition in our teams, and all team members must have the same information and must have same definitions around this concept. So the transparency in software architecture measuring is really important. That's why we say that viva transparency, because without transparency, of course, our software architecture might be very weak, and it might not be help our overall software design as expected. In order to measure the software architecture characteristics, we have different mechanisms. One of that methods is operational measures. Of course, we can use operational measures only for the characteristics or only for measurements which have obvious direct measurements we have defined for them. For example, we're talking about performance or we're talking about scalability. We have some criteria which we can measure them. We can plus some numbers together. We can use different statistical methods and find a result or find our final measuring result. The main problem while working with the numbers, or main problem when we are working on operational measurements, is the fact of outliers in our data. Of course, when, for example, suppose that we're going to measure the response time of our applications, which might be about measuring the performance and scalability of our applications. When we're working the response time, we might have some data set. For example, you see that we have some data set here. The majority of numbers is around 1, but we have one number which is around 10,000. If we decide to use the average statistical methods to analyze this data, of course, our final result will not be true because the majority of our data is equal to 1, but one of them is equal to 10,000. Okay, we're going to use the average statistical method. Average. What does average means? Average means that the majority of data is around some value. Okay. Suppose that we have 3 1 and 1 10,000. The sum of these values is about 10,003. Okay, and then dividing it to 4 will result in a value which is around 10,000. It means that it's around a value which is not equal or which is not near the majority of our data. So the 10,000 here is our outlier data. We need to find that outlier data, omit it from our analysis, and calculate our final result without the outlier data. I mean that we need to ignore the outlier data, of course. We're not going to totally remove the outlier data. The outlier data here is very important to us. But in order to calculate the average, as we assume that we're going to use the average statistical method to analyze our data, we need to ignore the outlier data. But in the further analysis, we need that outlier data, of course. As you see that using that, the same data set, sorry, using the same data set, we calculate the average response time is equal to 1, but we are aware that our minimum response time is equal to 1 and maximum response time is equal to 10,000. So we're not omit that. We're not remove the outlier data. We just ignore it in order to calculate our average data using this mechanism while measuring the characteristics and operational measures. We have our average that's preserved, and we have more data to be aware of, which could be very useful to analysis and to measure. As you see, while we're working with operational measures, we were working with statistical analysis, and we're trying to build our statistical models. While we have our statistical models, of course, in the first stages of creating the statistical models, our model might be failed or it might not be fit very well into our data. The main reasons for failure of our statistical models is based on that the model is incorrect or something is amiss. Both which teams likes to know in order to make their statistical models better and to evolve it over time. Of course, after some portion of time, we will have a very good statistical model which can fit into our data and which can gives us a very informative information about our characteristic measure. This is overall, this is what the operational measures work, but not all the software characteristics are. We're not able to, of course, measure all the software characteristics using operational measures. Some of the characteristics are structural measures, which are not so obvious, such as performance, or which are not obvious, which is not obvious as performance. For example, the complexity. When we're talking about the complexity or the code complexity, we have no operational measure to measure, or we cannot design a statistical model to analyze the code complexity. This is where the cyclomatic complexity comes into game. Using the cyclomatic complexity, we can calculate the total complexity of our code, and of course, we can get into the numbers. We can again do our operational measures or do any other statistical measures. But the problem here is to create that numbers. About the cyclomatic complexity, we all know that the complexity, of course, is a code smells, might have a hardware related, might be affect our deployability, testability, or other software characteristics. We know that the complexity, of course, is not a good thing in our code. We should prevent the complexity in our code. Before we can prevent the complexity in our code, we need to calculate the complexity in our code. So let's see how we can calculate the cyclomatic complexity in our code. It's not very hard, of course. There's some formula to calculate the cyclomatic complexity in our codes. One of the very well-known formula is the CC is equal to E minus N plus 2 multiplied P. E is our number of the edges in our follow graph, N is our number of nodes, and P is the number of connected components, or let's say that it's number of methods in our code. Without any other descriptions, let's dive into some samples to calculate the code complexity in some sample codes. Before moving forward, there are 2 points to note. That's when the exit point is directly connected back to the entry point. Of course, our methods are linear methods. The exit point is directly connected to the entry point. Then we can omit the 2 before P, and our formula can be simplified as E minus N plus P. Or when we are talking about a single method. We are going to calculate the code complexity in a single method. We can omit P, and our formula can be simplified as E minus N plus 2. About calculating the cyclomatic complexity in class, we can use the average complexity between all methods in that class. That's how we can calculate code complexity in a class. Okay, that's okay. And the final point to note is that's the use case of the complex cyclomatic complexity. I mean that where it can help out. One of the obvious use cases for the cyclomatic complexity is that the cyclomatic complexity denotes the number of unit tests required for the code. It's very informative to developers while they need to find out how many tests they should write for their code and how they should design their unit tests in order to cover the whole code or in order to cover the whole business. Cyclomatic complexity can help them in that position too. For example, suppose this code, we have a code which is very simple. A is equal to 10, some if condition here. If B is greater than C, then A is equal to B, else A is equal to C, then print A, B, C. Okay, in order to calculate the cyclomatic complexity for this code, one of the methods is to design the flowchart of our code. We have a start point here and end point here. After starting, A is equal to 10. Each of these shapes are our N in the formula, are there our node in the formula which we discussed about it. And each of these arrows is the edge in that formula, okay? We have A is equal to 10. And we have a condition node here, B greater than C. It might go to A is equal to B, or when B is not greater than C, A is equal to C, and then print and finish. Okay, how many nodes do we have here? We have 1, 2, 3, 4, 5, 6, 7 nodes. Okay, and how many edges do we have here? I mean, how many arrow we have in this flow chart? Let's count the arrows. We have 1, 2, 3, 4, 5, 6, and 7 edges here. What was the formula? Formula was E minus N plus 2 multiply P. E is 7, number of edges, and again is the number of nodes, which is again 7. 7 minus 7 is equal to 0 plus 2 multiply 1. Why 1? Because we're going to calculate the cyclomatic complexity in single method. It's the single method that we're going to calculate. The P is equal to 1. The final result, or our CC, or cyclomatic complexity in this code, is equal to 2, which it means that we need 2 unit tests to write in order to cover this code. It's very simple. We need 1 unit test to test that the B is greater than 0, and we need other unit tests to cover the B is not greater than 0. It's very easy to calculate cyclomatic complexity and get many information from the code and the other information. Okay, let's move on to the other example. We have some other code. We have if condition here, which there's another if nested inside it, and something else. Okay, let's create the flowchart for that code. We have a start and finish point here. A is equal to, there's a condition point. If A is equal to 345, then the B is greater than 0 is activated. Otherwise or else the print A route is activated and the code goes on. Okay, what's the code complexity here? I mean, what's CC is equal in this code? It's very easy. Let's count the nodes: 1, 2, 3, 4, 5, 6, 7. And the number of edges, it's 1, 2, 3, 4, 5, 6, 7, 8, I think. Plus 2 multiply 1. As you see that 8 minus 1 plus 2 is equal to 3. We need 3 unit tests to cover this code. Of course, if the cyclomatic complexity, whenever the cyclomatic complexity arises, it's increasing, it means that there are some depth, there some technical depth inside our codes. The greatest the cyclomatic complexity, the weakest the code structures. It's very important to note that. It's not good point. For example, we have a code with cyclomatic complexity equal to 100, and we say that, yeah, you see, my code is very complex and I'm the superhero of the thing. No, if the code's cyclomatic complexity is equal to 100, it means that the code is super weak code, and there are many technical depths inside that code, and we need to refactor that code. The lowest is cyclomatic complexity, the strongest the structure of codes, and it's very good to have the lower cyclomatic complexity inside the codes. Let's move on to other example to calculating cyclomatic complexity. We have another simplified formula to calculate cyclomatic complexity, which is denoted as CC is equal to P plus 1, where the P is number of predicates nodes contains in the control flow graph. Without drawing the flow chart, counting the nodes, or counting the edges, we can calculate the cyclomatic complexity of our code. Of course, not all our codes are that simple that we can draw the flow charts for that for our codes and then start counting the nodes and edges. It's not very easy to do this in our codes or in our code evaluation. This formula, CC is equal to P plus 1, is very functional and is very useful. P is the number of predicates nodes contains in the control flow of code. Okay, we have some codes here. There are many lines of codes here. It's not very important. Let's count the number of predicates lines in our graph. We have one predicate line here, while index is lower than or equal to n minus 1. This is condition node 1. We have another predicate node here. It's not important that the predicate nodes are nested or not. It's not important while using this formula. We're just going to count the predicate nodes without paying attention to the nesting level of them. Okay, we have n person next is equal to 0. It's conditional node again. And we have the third predicate node here, which is index is equal to n. This conditional node number 3. So what's our cyclomatic complexity? Easy, P plus 1. P number of predicates nodes is equal to 3. 3 plus 1 is equal to 4. We need 4 unit tests. We need 4 unit tests to cover this code. Or in other definition, we can say that there are 4 different routes to execute this code. One of the very important definition of cyclomatic complexity is the number of routes to execute that code. Cyclomatic complexity here is 4. It means that we have 4 different and 4 unique routes to execute our codes. Of course, when we have 4 unique routes, it means that we need 4 unit tests. We need to write a unit test. We need to write a unit test for each our unique route. It's very easy. Okay, let's go to other example. Oh, we have another code here. Oh my God. There are something in the screen. I'm not going to read the code at all. Let's calculate the cyclomatic complexity here. Oh, we're going to find out another method to calculating cyclomatic complexity. We can put line numbers in our codes, starting from 1 to 15, for example. Of course, the variable declaration lines are not counted. Let's see how this one works. We have line number 1, 2, 3. They're all executed sequentially. There are not predicate nodes here, so it's not important. We put 1, 2, 3 in same shape. After executing 1, 2, 3, we're going to line number 4. In line number 4, we have 2 options. We can jump into line number 13. We can jump from line number 4 to line number 13 if the index is not lower than or equal to n minus 1. Then we will jump into line number 13. Or if the condition is correct, from line number 4, we will jump into line number 5 and line number 6. And this analysis continues until we reach the end of our method. So how we can use this graph to calculate the code complexity? E minus n plus 2 multiply p. How many edges do we have here? Let's count the arrows. We have 10 arrows in this shape, and how many in this graph? And how many shapes do we have here? We have 8 shapes. 10 minus 8 plus 2 is equal to 4. Without using the graph, we can use the previous formula, p plus 1. How many predicates do we have? We have while, if, another if. We have 3 predicate plus 1 is equal to 4. Our cyclomatic complexity code is 4. Again, what does it mean? It means that there are 4 unique rows to execute this code. It means that we need 4 unit tests to cover the all execution rows in this code. Let's see other example. It's very easy to calculate cyclomatic complexity in this code. Of course, this code example is the GATE CS 2004 exams questions. Let's calculate the code complexity in this example. We can draw the graph from line number 1. We have option to jump into line number 6, or we can further the execution to line number 2 or 3. Again, from line number 2 or 3, there's a if condition there. We can jump into line number 5, or we can further to line number 4. We reach the end of our lines. What's code complexity here? Number of edges minus number of nodes plus 2 multiplied p is equal to 3, or p plus 1, number of predicates. How many predicates do we have in the screen? While and if we have 2 predicates plus 1 is equal to 3. Our cyclomatic complexity in code is equal to 3. Let's see another example where we have a loop here. What's our cyclomatic complexity here? It's not important that we have 4 in our code, or we have an if condition in our code, we have switch expression. They're not totally important. The predicate here is the key to calculate the cyclomatic complexity. How many predicates do we have in the screen? Predicate number 1 over 4. Predicate number 2, A is equal to B. It's very important to note that when we're going to combine the if conditions using and or expressions, they will be counted as separate predicates. Okay, predicate number 2, A is equal to B, and predicate number 3, B is equal to C, and the final predicate, else if A is not equal to B. When we have else if in our code, it will be counted as a predicate. But if it was else only, it's not predicate at all, because else predicates is counted in the previous if statement. So here in this code, how many predicates do we have? Predicate number 1 for 4, A is equal to B, B is equal to C, and A is not equal to B. We have 4 predicates in the screen. The cyclomatic complexity is equal to 5. Example of calculating cyclomatic complexity. We have some code here. Oh my God. Of course, I'm not going to read this code, but my colleague comes to me and asks me that whether this code is good code or not, whether this code is complex code or not, whether this code, is there any technical depth in this code or not. I need to calculate different measures. One of them is cyclomatic complexity. From cyclomatic complexity viewpoint, I can say that this code is complex or not, but I need to quantify this qualification. In order to calculate cyclomatic complexity, p plus 2, 1 number of predicates for each 1, if, 2, and the third if here, 3. We have 3 predicates, 3 plus 1 is equal to 4. So from cyclomatic complexity view of point, I can say that this code is a good code. It's not very complex code. Again, I'd note that from cyclomatic complexity point of view, this code is not complex. We have other measures to consider when we're talking about technical depths. There are many different measures we need to calculate. One of them is cyclomatic complexity. The other one is lines of code, the depths of inheritance, and the other factors we need to calculate and paying attention to them. But from cyclomatic complexity points of view, this code seems to be good code. But from lines of code, if I need to analyze this code from the point of view, of course, this is not good code. Okay, what's good value for cyclomatic complexity? Of course, finding the good value for cyclomatic complexity have direct relation with the problem area we're working on. Sometimes we're working on a problem, on a complex problem, which has only one complex solution. So when we have no other way to solve a problem other than that complex solution, then the high cyclomatic complexity for that solution would be okay, which can have a solution with lower cyclomatic complexity, but we achieve the cyclomatic complexity with the high value. Of course, our final result would not be a good result. But totally, as a rule of thumb, we can say that if the cyclomatic complexity is between 1 and 10, it's a good code. The structure of code and the it's well structured and well written code. The code is high testable and the cost and effort is less. It's a rule of thumb. It's a rule of thumb. It might be different from a project to the other project. When the complexity is between 10 to 20, it means that, okay, we have some problems in our code. The testability is going to be affected in a negative manner, or the cost and effort is medium. If it's between 20 and 40, it means that we are facing very complex code. The testability is low, cost and effort are high. And if the cyclomatic complexity is greater than 40, it means that's okay. The code is not at all testable, and we're facing with an electronic garbage. We need to, of course, refactor that code. Again, I'm going to get back to my first expression. The desired range or the desired value for cyclomatic complexity is directly related to the problem and solution area. These numbers, these range, are rule of thumb, are some things to be considered as best practice, for example. They are not hard rules that we should apply them on all projects. No, they're rule of thumb. Their range might be smaller or bigger in different projects. The final method to measure the architecture characteristics is the process measures. Some other architecture characteristics are composed of many other architectural characteristics. For example, as I said, in the agility software architecture, the agility might be composed of testability and deployability. We need to measure testability and deployability in order to measure the agility in the top level. Okay, testability can be measured through the code coverage testing, and we can gather the result from code coverage testing. Okay, but in order to calculate the deployability, again, we might need to calculate some other inner software architecture characteristics, such as the successful or failed deployments. We need to measure the rate of successful or failed deployments. After measuring deployability and measuring testability, we can finally measure the testability in our software. So we need to measure the whole process in order to measure our architecture. In order to sum up the discussions in the session, we introduced the 3 different measuring methods to measure the software architecture characteristics. The operational measures, for example, performance, which we're going to using the architectural models or architectural methods. Structural measures, for example, using the cyclomatic complexity. There are many formulas and methods to calculating the cyclomatic complexity, and the third method using the process measure to calculating the software architecture characteristics. I hope that this session was be informative for you. In order to contact me, you can use v.farahmandi@jinget.ir in order to send me your emails, or you can find me in GitHub using Vahid Farahmandian. You can find me using v.farahmandian on LinkedIn, Vahid Farahmandian in Instagram _Jinget in Twitter or X. You can read my blog post in jinget.medium.com, and you can watch my videos in YouTube using jinget.net YouTube channel. I